Hi guys, here's another video about the CSS Pure Mathematics Exam from 2023. This is section C, and we are going to solve question 8, item B. This is the last question of the exam, and it asks us to find the residues at the singular points of the function given by this expression we have here, which lie inside the circle given by modulus of z equals 2. So let us begin. First, we take a look at the expression which defines the function. So we look at it's a rational expression, so I look at the denominator. We see that we can factor the denominator as this, z times z minus 1 times z minus 4. This tells us that the singularities of the function, which I'm calling f, are 0, 1, and 4. And since the modulus of 4 is greater than 2, the only singularities of f which lie inside the circle given by modulus of z equals 2 are 0 and 1, as we can see here. So here inside the circle I have 0 and 1, and outside of it I have 4. So we will only find the residues at the points 0 and 1. Okay, now let us proceed. So we have f with this expression here, and we know that this denominator can be factored this way, and we are going to use this to construct two auxiliary functions. So here are the functions. I have this function g defined in the open disk centered at 0 of radius 1/2, which takes z into z times f of z, which has this expression. I have the same numerator as before, but the denominator is just z minus 1 times z minus 4. And I have this function h defined in this open disk centered at 1 and of radius 1/2, which takes z to the complex number z minus 1 times f of z, which is the same as this expression. So I have the same numerator as before, but the denominator is z times z minus 4. So we look at these two expressions and we see that g and h are analytic in the domains I define them, because I have no problems in their denominator and their rational functions. So I can write both functions as Taylor series. I can expand them using Taylor series. So I can write g as its Taylor series about 0, and I can write h as its Taylor series about 1. And I have these expressions here. Okay, now, and I'm going to use g and h to find the Lorentz series of f about 0 and 1. So let us proceed. So for every z in the open disk centered at 0 of radius 1/2 minus the point 0, we have that f of z equals g of z divided by z. But g is given by a Taylor series. So I just divide, since I'm dividing the Taylor series by z, I get this expression. And I can rewrite this expression by, instead of beginning at 1, starting at 1, I start at minus 1. So this expression is the same of the sum going from minus 1 to infinity. And since I put a minus 1 here, I have to add 1 here and 1 here and here. So I get the derivative of order n plus 1 at 0 divided by n plus 1 factorial times z to the power n. But I can write this as this. So I just take the part minus 1, it's g of 0 over, because when n equals minus 1, I have minus 1 plus 1, I have 0, and by definition, when I have 0 here, it's just the function, so I have g of 0 divided by z plus this summation here. And in a similar way, for every z in the open disk center at 1 and of radius 1/2, leaving out 1, we have that f of z equals h of z times z minus 1. And since I had h written as a Taylor series. I just divide it by z minus 1. I get this n minus 1 here, which again I can rewrite this way. So I just change the index. So as before, this becomes the n plus 1 order derivative. Here I get n plus 1 factorial and the z minus 1 to the power n. And as before, I can rewrite this expression. I just take the part with the index minus 1, put it here, and here I leave the other part as a series. And with this, I managed to find the Lorentz series of f about 0 and the Lorentz series of f about 1. And by definition, the residue of f at 0 and at 1 are just the complex numbers which occupy the part, the minus 1 slot. So it's the one, the real number multiplied the 1 over z. So the residue of f at 0 is g of 0, and the residue of f at 1 is h of 1. So this is what we get here. Now I just have to plug the value in the expression for 0 in g and 1 in h. And I get this. So the residue of f at 0 is 2, and the residue of f at 1 is 5. And we are done. Thank you very much. I hope you enjoyed this video. Please give me a thumbs up, subscribe to the channel, and I hope to see you in the next series of videos about mathematics. Thank you very much. Bye.